Okay, welcome to C1 Part 2. Last lesson we finished up at the bit about cracking, polymerization, etc. What we're going to be looking at now, okay, is paints, pigments, etc. Okay, so let's just get this started. Okay, so like I said, we looked at recycling in the last one. We're going to look at cooking food now. Okay, now this all starts from cooking. So when you cook food, you can't go back to the way it was before. Why? Because it's gone through a chemical change. Now that's what you need to know. Why you cook food, it goes through a chemical change. And what you need to know is that that is irreversible. Irreversible means it cannot go back to the way it was before. Okay, this is obviously an egg, an uncooked egg, and when you cook it, it obviously changes. Okay, now you can see the changes that have happened here. The egg white protein has gone from being clear, okay, to solid white. Okay, that has obviously gone through a chemical change because we can't turn this back into this. Yeah, chemical change, irreversible. Okay, now the thing that you need to know about the egg is that the egg contains proteins, and proteins have definite 3D shapes. Okay, like this. This is albumin. Okay, now, like I said about albumin, it's unchanged. It looks like a certain shape, but once it's been cooked, the protein changes from the specific shape it should be into an inactive shape. Okay, so which basically means that the protein has been something called denatured. Okay, so the protein, when it's cooked, it becomes denatured. Okay, that's really all you need to know about that. Obviously, you'll know when you've cooked a potato and it'll go soft and fluffy, which is also a chemical change and it's irreversible. Okay, now looking at these fairy cakes, which one contains no baking powder? Well, it's obviously this one. Okay, because baking powder allows cakes to rise. But what we need to know about cooking chemistry is why. Okay, how does baking powder make cakes rise? Okay, how does it do it? Well, it does it because when you put baking powder in a cake or anything else like that, you heat it up and the baking powder breaks down and gives off carbon dioxide. Now that carbon dioxide makes the cakes rise. Okay, now the scientific name that you need to know for baking powder is sodium hydrogen carbonate. Okay, obviously the purple ones are yellow, are sodium. You've got the carbon and the oxygens right there. Not sure where the hydrogens are in this diagram, but that's the chemical name of baking powder, and you need to know it. Sodium hydrogen carbonate. Okay, so when you heat the baking powder, or sodium hydrogen carbonate, we break it down when we heat it, and that process is called thermal decomposition. Okay, now as you know, the word thermal means heat, and the word decomposition means breaking down. Okay, so what do you think is made when sodium hydrocarbonate breaks down? Well, we've already covered that because it makes carbon dioxide, which makes the cakes rise. Okay, so this is the word equation for this. Sodium hydrogen carbonate, okay, and then you've got the arrow, and it makes sodium carbonate, carbon dioxide and water. Now this is the word symbol equation for this. You do need to know this even for the foundation tier. So it's sodium, okay, which is right there. Okay, so it's sodium, yeah, hydrogen, yeah, and this CO3 is the carbonate. Sodium hydrogen carbonate, and this makes sodium, and remember the CO3 is the carbonate. Okay, so it makes sodium carbonate, carbon dioxide and water. Now you need to make sure that you know that chemical symbol. Okay, make sure you know the equation. Right, okay, so because sodium hydrogen carbonate gives off carbon dioxide, we need to be able to test for that. Now, obviously, you all know the test for carbon dioxide. It is bubbling it through lime water. Now, this lime water is obviously going to turn cloudy white. Okay, and that's going to confirm the presence of carbon dioxide. So there you've got the baking powder, or sodium hydrogen carbonate. Okay, and the lime water test for the CO2 that's going to be given off, and you can see that there, there, and there. Okay, so we use lime water to test for it. It goes milky white, like I've just told you. So this, when CO2 is added to this lime water, that's the cloudy white that it goes. Okay, now additives are added to food, and it basically preserves them. Okay, but it does a lot more than that. There are different ones. For example, flavorings, which obviously give the food flavour. You've got something called emulsifiers and stabilizers, and you've got preservatives and antioxidants. Okay, and obviously colorings. Okay, let's just have a very, very quick look at all of these. So antioxidants, basically they preserve the food by stopping them from reacting with oxygen. Now, if you cut an apple open and you just leave it there, it'll start to go brown. And it'll start to go brown because oxygen is reacting with it. Okay, and so what scientists can do is they can add an additive called an antioxidant called vitamin C. Okay, otherwise known as E300. Okay, and that absorbs the oxygen and stops it from reacting with the food. Okay, always are added to things like, for example, when you buy packaged sandwiches, they'll always have vitamin C added to it because obviously oxygen makes the bread go stale, and they want the bread to remain as fresh as possible. So the first additive that we add to food is antioxidants. Second one's colorings. It's pretty simple. They give the food, they improve the appearance of the food, the visual appearances. And you can add cochineal to it, which is red colouring, which actually originally came from cochineal beetles, but now, today, is made synthetically. You've got emulsifiers. Now, water and oil don't mix, and emulsifiers allow water and oil to mix to stop them separating out. Okay? Preservatives, just as the name suggests, preserve the food to stop it going off. Okay, some typical examples are E330 and E220. Okay, now citric acid and sulfur dioxide can be an example of them. Yeah, right there. Flavorings, they enhance the flavour of the food. Now, if everyone eats a lot of Chinese food tends to contain a lot of something called MSG, which is monosodium glutamate, and what that does, it makes your tongue more receptive to taste. It actually makes the food taste better. Okay, and gives it more taste. Stabilizers, they basically just stop their food from breaking down and maintaining its structure. Okay, so you add emulsifiers, and to be honest, most of the time you find them in things like ice cream, things that normally break down, or trifles, etc. And locust bean gum is an etc. of one that might be used. Okay, so those are the main types of food additives that you would get. Okay, I can't seem to go to the next page, so let's get rid of this, get back to the arrow, and then I can select it. There we go. Alright, I'm just going to solve that to save a little bit of time. Okay, those are all the things that it does. You're more than welcome to pause the video and have a read in case you're not too sure of what it does. Okay, same thing with this. Have a go. Turns brown, fruit salad turns brown. Which one? Antioxidants. Takeaway meals, leaving the customer wanting more. That's going to be flavour enhancers. Food that contains oil and vinegar like mayonnaise, that's going to be an emulsifier. Sweets designed to attract young children. Well, children like brightly coloured sweets, so it's going to be food colouring. Okay, now emulsifiers, this isn't very clear, but emulsifiers, like I've already told you, allow water and oil to mix. Okay, now water and oil normally don't mix, so that's why you add the emulsifier. And an emulsifier is made up of two parts. Okay, it's made up of a head and it's made up of a tail. Now, the head of the emulsifying ingredient, okay, is hydrophobic. Okay, which means it's scared of water, so it likes the oil. Whereas the tail is hydrophilic, okay, which means it likes the water. Now, those names might sound a little bit complicated to you, but they're really not. Hydro, okay, just stands for water. Okay, that's all the hydro stands for. Okay, the word philic, okay, means like. The word phobic means hate. So obviously, hydrophobic means it doesn't like water. If it doesn't like water, it means it likes oil. Okay, hydrophilic means it likes water. So if it likes water, then it doesn't like oil. So these two bits connect the oil and the water together. Okay, now moving on to solutions. Okay, when a solid, I think I'm going a little bit fast, so I think I'm going to try and slow down. I think I'm trying to keep the video timings as short as possible, but I think I best slow down. When a solid dissolves in a liquid is called a solution. Okay, now the solid that actually dissolves in the liquid is called the solute. Okay, the solute. Okay, that's anything like salt, sugar and coffee, etc. The liquid that it dissolves in is called the solvent. So the solute plus the solvent equals solution. Okay, now sometimes a solute, okay, that's the solid that normally does dissolving, doesn't dissolve in that particular solvent, and we call that insoluble. Okay, now sand is insoluble in water, like you need me to tell you. Right, now nail varnish. Okay, now nail varnish is a liquid that will pretty much, when it dries up, it will turn solid, and it's a solute. Now, does it come off in water? No, it doesn't. And the reason being is nail varnish is insoluble in water. Okay, that's why you use a nail varnish remover. Anything that contains an acetone or an ester would be the correct solvent for that particular solute. Okay, so water won't get nail varnish off. It has to be the correct solvent for that particular solute. Okay, now this is just some examples of some stains and the correct solvents that will get them off: blood, water, oil, methylated spirits, nail varnish, propanone, wine, salt water. Oh, does salt water get them? Okay. Right, now on to paintings. This is one of the first ever cave paintings from years ago. How old do you reckon it is? Very, very old. I can't remember what the number was now. Is it 30,000 years? I can't remember now. But anyway, these are just a few examples of cave paintings. So how did those cave paintings stick onto the wall? Well, the reason I'm showing you this is because you need to know about paint. And you need to know about the three bits that paint actually have inside them. Now, paint contains three things. Okay, first of all, it contains a pigment, which gives the paint its colour, i.e. coloured rocks. Binding medium sticks the pigment to the surface, which is going to be the oil. Okay, and then you've got the solvent. Now, the solvent makes the paint runny, so we can spread it over the surface. So those are the three things that a paint has on it. Okay, now there's two kinds of paints I'm going to teach you about now. There are oil-based paints and there are emulsions. Okay, now this is an oil-based paint, and you can see from this diagram that the pigment is obviously the colour bits in the paint. Okay, and you've got a binding medium and a solvent in there. Now, when you apply this to the surface, what's going to happen is that the binding medium and the pigment are going to stick to the surface, and the solvent is going to evaporate. Because remember, the solvent is just there to make it runny. But once the solvent evaporates, okay, it leaves behind the binding medium, which is the oil, and the pigments inside, which obviously gives it its colour. And you can see that these dots are the pigments, the liquids are the binding medium and the solvent. Pigment provides a colour, oil protects the surface, and the solvent evaporates, and you can see that. So an oil-based paint applied as a thin layer, solvent evaporates, and the binding medium forms a skin which sticks the pigment to the surface. Now, the other one is an emulsion. Now, as I've already taught you earlier on in the series, that oil and water normally don't mix unless you have an emulsifier. Okay, now, so with this, an emulsion, okay, is where you get the oil, but you put pigments in it. Okay, so can you see these droplets of oil inside the water? Now, these droplets of water contain pigments inside them. Now, when you spread it onto the surface, okay, what's going to happen is that instead of a solvent evaporating, which is the normal chemical solvents, water as the solvent is going to evaporate instead. And that, just like before, it's going to leave oil with the oil, which is the binding medium, and the pigment behind. Okay, so emulsion paints, the key thing is that they are water-based. Okay, small amount of oil, water is the solvent, and the pigment's inside the droplets of oil. When the water evaporates, it leaves the pigment, or the oil and the pigment behind. Okay, now that leads us on to special pigments. Okay, now special pigments, there are two. Okay, there's thermochromic and they are phosphorescent. Now people always confuse the two together. Okay, now let's deal with thermochromic pigments first. Now the word thermo, okay, means heat. Okay, now, or temperature. Okay, now chromic means colour. So obviously thermochromic paints are heat pigments, aren't they? So they will change colour according to the temperature. Can you think of any uses for them? Well, baby spoons are one example, in that they will turn different colours depending on how hot the food is. Obviously the baby can't tell you this is too hot, it's just going to start crying, but you can save yourself the bother by having a spoon which changes colour, which will let you know if the food is too hot for the baby. Same thing applies to toys which go in the bath. Okay, and they can obviously tell you how hot, if the water is safe for the baby or not. Okay, and some novelty uses when mugs can change colour according to the temperature. So obviously put some hot coffee in there and it will change colour. Okay, what is this? This is obviously, as you can see, is glow in the dark. Okay, we don't call it glow in the dark, we call it phosphorescent. Okay, now phosphorescent is glow in the dark, so what it does is that it absorbs light energy, okay, and stores the light from daylight, and then it gives it and releases it at night. Okay, that's basically what it does. Can you think of any signs, any uses? Well, fire exit signs are one typical example of phosphorescent pigments. They'll absorb light energy during the day and they will release that during the night. Okay, yeah, so obviously if you had one of these signs locked away in a cupboard, it won't be glow in the dark because it won't have an opportunity to absorb any light energy. Okay, so if you ever get a question like this, Billy leaves his glow-in-the-dark watch in the cupboard and finds it won't glow in the dark. Why is that? The answer is that it hasn't had a chance to absorb any light energy, so it can't give any light energy out. Now, this is a very quick look at the old kind of style of glow-in-the-dark watches, in that they used to be used from radioactive materials. Okay, and you used to get adverts for them. Years ago. I did have a picture of a radioactive watch. I'm not sure where it's gone. But anyway, so that is actually the entire unit. So I finished that sooner than I expected. So this is part 2. I hope that made sense to all of you guys. If you watch this, make sure you watch the others. Okay, alright, thanks then. Bye.